Sweet. Hi, you guys. I'm going to go over the Chapter 6 worksheet with you guys just because I feel like I didn't do a good job explaining it last time. So, yeah, let me actually get Zoom up on my iPad. Forgot about that. Totally messed up. Start. Just go in. Okay, continue. Just gonna keep writing.
I hated that. I hated every second of it. Okay, so let me share my screen. Start broadcast. Okay, so now I'm gonna go over this worksheet. And I'll send you the link of me actually doing it as well. So then, not the link, the thing of me doing it, or the finished worksheet, so then you guys can see. If you want to hear me explain it, then this is what this is for. So, okay, this is not tiny enough. Okay, so we're looking at all of these things, and we're looking to see if they're strong electrolytes or weak electrolytes, and if they can break apart. So we have to think about, what is a strong electrolyte? So a strong electrolyte is a strong acid, strong base, or it's a salt. And then a weak is just like a weak acid and a weak base. So, and so then the next thing that you would do is you have to remember those things you had to memorize. So if we were going through, and first thing we're going to do is figure out if it's strong or weak. This is a strong one. This is a weak one. This is a strong one. This is neither. It's a non. I did not spell it right. Electrolyte. So that means that it's not going to break down. There's not going to be a formula for it. So it's just going to be CHO3 or CH3OH. This one here gets to fully break apart. So it's going to break apart into K plus, and which is aqueous, and CO3 2 minus, which is also aqueous. This one is weak, so this one's weak, so it's gonna break apart, so we can make an equation, but it's not going to break apart as fully. It's not going to be as great. So I think in a problem like this, the best thing you could do is, if you're not sure if it's a strong or weak electrolyte, just go ahead and write out what it's going to break out into. And the way you can tell, like, if I was going to write the problem, like, oh, is it this? The way that you can tell the difference is that K2CO3, it's just going to break apart. It's going all the way. The reaction's fully going that direction. And here, hello, don't do that to me. Here the reaction, oh, dang. Here the reaction is only partly going that way. HNO2. It's going back and forth. It's in equilibrium. That's also what it's called. But it's going back and forth between being fully apart and fully together, and that's why it's very weak. And this one is the same thing. It's going to completely dissociate. That's why it's full arrow going one way. It can be H plus and NO3 minus. Okay, so then we have to make so many of these. We have 400 milliliters and 1.1 molarity. what is the mass? This is where we're doing a lot of conversions. I know that we did conversions. I like to do a little roadmap for myself. So like the first thing you need to know is you need to figure out, we need to convert milliliters to liters, okay? And then we need to find out the moles from the molarity. So molarity is moles over volume. So I tend to do liters, it's just easier that way. So 400 milliliters to liters is going to be, you move it 1, 2, 3, you divide by 1,000. So it's going to be 0.4 liters. So that would be, we have to rearrange. We have to rearrange this to get moles by itself to be moles is equal to molarity times your volume, which would be 1.1 molars, or 1.1 molarity by 0.4 liters, and that's 0.44 moles, and then you have to convert that to grams, so 0.44 moles. You have to find the molar mass of this. I know that it's 85. I'm going to be kind of fast. So 1 mole of NaNO3 is 85 grams of NaNO3. Just about that, and you're going to get 37 grams of NaNO3 is in this 1.1 molarity solution. So then if you're diluting something, like the key word here is diluting. Any sort of dilution involves M1V1 is equal to M2V2. That's like a little hint to yourself, like, hey, this is what I should be doing. So that's what that is. So then we know, think what's M1? Molarity 1 is going to be 4.8 molar. V1, your volume 1, is 3.5 liters. I'm getting this from the word problem. M2, what is that? Well, I don't know what that is. I'm trying to find that, so I'm going to put a little question mark to it. V2, what is that? Well, it's right here. It's 45 liters. So then I have to rearrange this equation to get M2 by itself. So that's going to be M1 V1 is equal to V2 divided by V2 is equal to M2. So then how I'm going to write it is 3.5 liters by 4.8 molarity divided by 45 liters is equal to 0.37 molarity. Okay. I like to box my answers so it's easier to find. Also, units are very important so you can see, okay, these units cancel out. The unit that's left over is molarity. I'm going to have molarity as my unit. It's a way to double check that you did the problem right. So then this one, I did a couple of times with one of my sections, so you should be really good at this one. But we have KNO3 and MgNO3 2. Overall, what we're trying to find, because we're mixing these two things together, we're making an aqueous solution. The new molarity that we're trying to find is of NO3. What's the concentration of NO3? Because that's the only thing they have in common. So that's what this solution is going to be of. So now that you know that, maybe this will make a lot more sense. So we have 100 milliliters and 1 molarity. We have 300 milliliters and 2 molarity. That's 0.1 liters. That's 0.3 liters. Overall, our total volume is 0.4 liters. Because we're mixing these two solutions together, we have to figure out what our total volume is going to be of our new solution. That's one of the steps. Another part of the step is that we have to find out how many moles of KNO3 and how many moles of MgNO3 is in each solution separately before we add them together. So then we can find okay, well, what's the concentration of the moles that, or how many moles of NO3 are we putting back in? So I'll do it in red and I'll make it a little bit bigger. Molarity is equal to moles over volume. So moles is going to be molarity by volume. Okay. So then if we do that, we have 0.1 liters by 1 molarity. That's 0.1 molarity, right? And then, or no molarity, 1.1 moles. This one's 0.3 liters by 2 molarity. That's equal to 0.6 moles. So then what we have to do is, now we know how many moles of each compound we're adding in to our new solution. Okay, let's pretend like, you know, we already add in the liquid for the solution. We got the total liquid going on over here. We know what that is. Okay, but what's the concentration of our moles going to be when we put it into this liquid that we've added all together? So then we have to go in and we have to divide this by 0.4 liters to get the new molarity. We're adding everything together. So that's going to be 0.25. I'm sorry, I got confused. And then this is 1.5 molarity. So then when we add everything in, so you can think about it like this. So this molarity is just of K plus, and this is of just Mg2 plus, okay? Because we haven't taken into stoichiometry yet. So we're using the things that we don't have in common, but now that we're putting them together, we have to add these two things together. Now I have to look at what we have in common. So it's going to be the same numbers, but different units. So it's going to be 0.25 molarity of of NO3, okay, plus 2 times 1.5 molarity of NO3 minus, and that's because we have a 2 right up here. We have twice as much. We only take that into account at the end, and that's how we get 3.3 molarity of NO3 minus. Put a little square around it so it's easier for y'all to tell. Okay, and then this part, these are your solubility rules. So let me write in what they are. NaNO3, which is aqueous, plus KCl, which is aqueous. There's no reaction. Right, like that. There's no reaction because everything in this is soluble. So everything and really the second half of the equation, your net ionic equation, is going to be the things that aren't soluble. And that's why in this case, because everything is soluble, there's no net ionic equation. There is no equation going to be added in. So this next one is NaCl plus Hg2C2H3O2. 2 of those is aqueous. This is aqueous. Okay, so I'm sure you guys can know how to balance the equation, so I'm going to leave that for you guys to figure out. But we have to think, you know, that, you know, this is going to react with this. Let me get it like a color going out. These two things together are insoluble. Okay, and remember, your net ionic equation, are things that are insoluble. So chlorine by itself is normally soluble, but Hg2 2+ is an exception for that rule. So your rules are really important. So the net ionic equation is Hg2 2+ aqueous plus 2Cl minus, because you have to balance that. That's aqueous is going to Hg2Cl2, and it's going to be a solid. Okay, so then the next problem, I'm having a fun time. I hope you're having a fun time. I hope you enjoy this. Okay, so then we have NH4 2SO4 aqueous plus SrCl2 aqueous. Okay, so then again, I'm going to leave you to do the balancing equations, but NH4Cl, which this and this, let me get color. This is good. This is soluble, okay? AgCl is insoluble because compounds containing Cl are normally soluble, but Ag is an exception, just like the last one. So, oh, was I reading the wrong thing? I'm sorry. I skipped to the next problem. I said the wrong thing. SO4 is insoluble because SO4 2- is usually soluble, but Sr 2+ is an exception. So this and this, when those mix together, is not soluble. That was my Family Feud noise when you get the X. It's like X, and it's like it's not on the board. Oh, I should do a study guide like that, like Family Feud. That'd be funny. That'd be fun. I may do that. I'm sorry, I have a problem. Anyways, okay, so I'm having a great time. We're having a great time at home watching this. Okay, so your net ionic equation for this one is going to be Sr 2+, which is aqueous, plus SO4 minus, which is aqueous. And because if you look right here, it's the same charge, they're gonna kind of cancel out because Sr2, SO4, 2, they can be simplified down to 1 because they're the same charge. Okay, so then that's gonna go to SrSO4. Heck yeah. Okay, so then, yeah, now I feel way better at explaining this. We have NH4Cl aqueous plus AgNO3 aqueous, and like I said, NH4Cl soluble, which I talked about the last one. Anything with NH4+ is always soluble, okay? Always. AgCl is insoluble, so let's highlight that again. That's a no-go. That's a no-go. Not soluble. Okay? It's not soluble because Ag is an exception. So then your net, I'm having a great time. Your net ionic equation is going to be the two things coming together. So Ag plus Cl minus. These are aqueous forms. Going to be AgCl S. So you're just going to have to remember these solubility rules just for this. I'm sorry if you don't want to. There's no other really way to explain it. So I'm sorry. Okay, so write a balanced chemical equation for any reaction that occurs. So potassium hydrate and magnesium nitrate. So we have KOH and MgNO3, 2, the charges or whatever. What is that going to form? Well, we know that we gotta do a little switcheroo, a little switch around. So OH and magnesium are gonna come together, and then your potassium and your NO3 are gonna come together, okay? And if you don't know the charges right off the bat, you can think about it like this. Okay, so let me get a nice color out. This is a 1. We bring that up here. I'm gonna assume the oxygen, that the OH is also going to have a 1 charge. There's an imaginary 1 here. I'm going to assume the K is going to have a 1 charge as well, okay? Let me zoom in, make that easier for you. There's a 2 here. Bring that across. We're going to assume that the Mg has a 2 plus. There's a 1, imaginary 1 here. We're going to assume that the NO3 has a negative 1 charge, plus, minus. So when we switch it around, it should be easier to tell, okay? So that gives us KNO3 plus, just aqueous. Gotta remember your solubility rules, by MgOH. It's a solid. I remember I had to do this for a lab. This was like a whole post lab. Was like, is it soluble? Is it aqueous? I did not do good on that because I was like, I don't know. No, I think I Googled it, actually, for my post lab, because I didn't know. Anyways, okay, so we have to balance this. So we have 2 NO3s over here and only 1 over here. So we need to add a 2 in front of that. Okay, well, now we have 2 Ks and only 1 K over here. So we need to add a 2. We'd have 2 out here. Well, now we have 2 OHs. We also have 2 OHs over here because magnesium has a 2 charge, so it works out. Woohoo! Yay! Okay, so when it says precipitate, that means solid. You gotta think in your head, what the heck? What is solid? What solid's coming from this? That is this. Wow! Amazing. Solubility rule is so important. Okay, so what is the mass of precipitant produced? We need to find the limiting reactant mass. And so that's where we have to go back to the word problem and find out how much you have. Oh, that's the erase button, not what I thought it was. Okay. Let me get a highlighter. You need to know how much you have of each thing going on. And that involves moles. So we have to, I'm going to write it the long way. You can go in and find moles through molarity and then catch back up with me. But so we're going to do Mg, let me do, we're going KOH to MgOH2, okay? And we should remember in our dearest heart of hearts stoichiometry that there's twice as many KOHs as there are MgOH, okay? Just a little side note. So if I have 0.1, 1 liters, we need to convert that. Did I? Yes. We're going to convert that to moles, 0.2 moles of KOH, okay? And then we have to remember that it's 2 moles of KOH for every 1 mole of MgOH2, 2 grams, 1 mole of MgOH2 by 58.32 grams. That's going to be 0.538 grams of MgOH2. Okay, mouthful. All right. So then we have to go from MgNO3 to MgOH2. I'm gonna take the lazy man way out and just like copy this. Don't hate me. Okay. Copy, paste, because I'm lazy. Okay. So then we're just gonna edit it a little bit. Again, it's 1.1 moles Gotta change the units a little bit. This is MgNO32, and it's actually a 1-to-1 ratio. Oh, I gotta change. Units are important. MgNO32. And that is going to be, because it's a 1-to-1 ratio, it's also going to change how much you have. So it's 1.17 grams of MgOH2. Okay, so that means, because whichever can make the least amount, that's your limiting reactant, because that's limiting how much product can be made. So oh heck no. So this is your limiting reactant. Yay, you figured it out. Woohoo! And only this amount can be made. Woohoo! That's the mass participant that can be made. Will you make that much? Probably not in your actual reaction, but you know, it's a good try. It's a good way to figure out like where you messed up. So to calculate this is a long worksheet. I just realized that this is a lot of work. Oh my god. Okay. All right. So we need to calculate the concentration of each ion in the solution. So we're going to have K plus, NO3 minus, and Mg2 plus. Left over, there's going to be no OH minus present because all of it's reacted and it's in the precipitant. If it was, because it's making the solid and it's not soluble because it's being formed into the solid, that's how we know that there's not going to be any of the ions left. So we need to calculate the number of moles of each ion after the reaction. So we have NO3 minus, it's 0.1 liters times 0.2 moles of MgNO3, 2 over 1 liter times 2 moles of NO3 minus over 1 mole of MgNO3, 2, which is 0.04 moles of NO3 minus. And then the volume is 0.2 liters, so we're going to divide it by 0.2 liters, so then we're going to have 0.2 molarity of this. And then pick a different color. For K plus, it's 0.1 liter times 0.2 moles of KOH by 1 liter. This is all kind of the same at the beginning. Then we have 1 mole of K plus for 1 mole of KOH. It's equal to 0.02 moles of K plus. And then again, we have 0.2 liters. We need to divide by 0.2 liters, which is going to be 0.1 molarity. So some of the Mg2 plus is unreacted because it is in excess. That's why that we still have some ions of it left. And so this one's a little bit longer. Yay. So we have to go through and figure out how many basically moles of MgNO3 is reacted with our mass over here. So that's what we're doing in this step. So they ask a lot of y'all. This thing's like a lot. Okay. So then to find Mg2 plus, it's 0.583 grams of MgOH2. It's 1 mole over 58.32 grams. It's 1 mole of MgNO3, 2 over 1 mole of MgOH2, which is 0.01 moles of MgNO3 reacted So then we can follow the same stuff as before up here after that because we know how much is reacted. So we have 0.1 liters by 1 liter and 0.2 moles of MgNO3 we have 1 mole of Mg2 plus and 1 mole of MgNO3 hello, that's going to be 0.02 moles of Mg2 plus is reacted. And then, so what you have to do is you have to take 0.02 moles minus 0.01 moles of, or this is how much is available to react. So you have to subtract 0.01 moles to get from this to get 0.01 moles of Mg that's unreacted. So then it's right above here. 0.02 minus 0.01. So then you have concentration Mg2 plus to 0.01 moles over 0.2 liters is going to be 0.05 molarity. Yay, look at that, amazing. So much time was spent on that. Okay, so, woo, how many more problems are there? A lot. I'm tired, I'm sorry. Okay, so then we have to write balanced equations, net ionic equations for these. So I'm not gonna balance them because y'all should know how to balance them. We've done that before. So I'm just gonna go from there to the net ionic equation. So this, what does that look like? That looks like HNO3, which is nitric acid, plus CaOH2, on the outside, 2, which is aqueous, goes to H2O, which is always a liquid, well, not always liquid, but it's going to be a liquid in this case. It's not going to be aqueous. CaNO3, 2, which is aqueous. So then this is what is going to be our net ionic equation. You need to balance it to figure out what you're going to have. That's going to be H plus, which is aqueous, plus OH minus, which is aqueous, goes to H2O, which is a liquid. So then this, we got to balance it and figure out what's going to happen. What's going to happen is that this is going to go to NaCN, which is aqueous, and water, which is a liquid. Then it's the same, oh wait, no, because you have to break it apart. It's not just like it's, so previously it's a strong acid. Nitric acid is a strong acid, so that's why in your net ionic equation, your H can be represented as an H plus by itself because it's very strong. It's a strong electrolyte. It's going to break apart easier. This is not as strong, so that's why your net ionic equation is HCN, which is aqueous, plus OH. It's not a strong electrolyte. That's why you have this here. Goes to CN minus, which is aqueous, plus H2O, which is a liquid. Okay. Almost there. Almost there. So then we have a sample of sulfuric acid that requires 24.16 milliliters of 0.106 molarity of sodium hydrate to complete neutralization with concentration of the original sulfuric acid solution. So But to figure out, first thing we need to do is we need to figure out the moles of the NaOH that's used to neutralize the acid. So then after that, we're going to write an equation, balance it, so then we can convert to how much sulfuric acid was used, and then we'll look at the total liquid to get the molarity. So I'll use this color. We have 0.02416 liters times 0.106 molarity for 1 liter is equal to 2.56 times 10 to the negative third moles of NaOH, because again we had the molarity. Why is she writing moles? Oh, okay. So this may be confusing for you, because you'd be thinking, how do I get to molarity? So if this is 1.6 molarity, then you think about it, I have a whole liter. That means I have 0.106 moles, and that's how you can make that conversion like that. Because that was confusing me as well. Sorry. So this is used to neutralize it. So then we have to write a balanced equation, which I'll go ahead and do. We have H2SO4 aqueous plus 2NaOH. Hello, just aqueous. Just going to Na2SO4 aqueous plus H2H2O, which is a liquid. Okay. So then back to this color. Then from there, because we know the stoichiometry, we can convert to our acid. So it's 2.56 times 10 to the negative third moles of NaOH by 1 mole, or nope, 2 moles of NaOH for every 1 mole of H2SO4, and that's 0.00128 moles of H2SO4. To calculate concentration of H2SO4, we're going to divide it by how much liters we had. So the liters is right here. That was a horrible color. Right here, that's what our liters are. Divided by 0.02416 liters, which is going to be around 0.0512 molarity. And that's your answer. Block it. Okay. So then we're going to do some amazing oxidation state work. How super cool and fancy. All right. So first thing we have is we have Cl2. We have to think, is it an element, an ion, or a compound? This is an element. So therefore, it's 0. That's what the oxidation state is. So then we have CuCl2. And overall, the charge is 0. So let's zoom this in. This is also a compound. We're zooming in. There's an imaginary 0 there. There's no charge overall. We can bring this 2 up because the 2 belongs to the chlorine, to the copper. This 1 here on the copper belongs to the chlorine. So you would know that the chlorine is equal to a -1 and the copper is equal to a +2. All right. The next thing is or a methyl CH4. And so once again, there's no charge. So this 4 goes up here to the carbon. This 1 goes up here to the hydrogen, which this is the part that could be confusing because carbon is all the way on the right side of the periodic table. It's a -4, and hydrogen's all the way on the left side of the periodic table. It's a +1. That's how many moves do I have to make to get to the near the noble gases. If you're on the far left, it's easier to go to the left and up to get to your nearest noble gas. That means it's a plus charge. If for carbon, it's faster to go to just straight to the right. That's a negative charge. It needs electrons. The left side, if you're going to the left and up, you can get rid of these electrons. You don't need them. So yeah, anyways, that's a good way to explain it, at least in my opinion. So then you have Cr2O7 2 minus. And so you can think like, this 2 belongs to the oxygen and the 7 belongs to the chromium. Is that what that is? I don't actually remember what the element is. So, and then because of the charge, like when it gets more complicated like this, you can think about it like this, where we have 2 times the +7 of chromium plus 7 of the -2s of oxygen. And this all has to equal -2. Or we don't really know what this is. We just know it's chromium, oxygen is usually -2. We do the math. Turns out that this is a +6 because we have to take an account for this negative. That's why chromium is going to be a -6 or a +6. Even though it would be a 7, we add it all together. You gotta get rid of it somewhere, you know. So then we have HSO4 minus. And again, we have hydrogen. We know it's a +1 for hydrogen, plus 4 oxygens, or -2s, which is for oxygen, plus something that's SO4 has to be, or something that's SSB, a -1 charge. And once we do the math, it turns out that S is also a +6. Okay, so then we have to determine that these are redox reactions. And you can do that by determining if any of the atoms change oxidation numbers. So obviously these aren't previously written. So PbNO3 2 aqueous plus Na2SO4 aqueous goes to PbSO4 solid plus 2 NaNO3 aqueous. And so these equations should already be given to you. I just didn't, I guess, copy it over correctly. But this is a little tip for your test. If you if you don't remember your solubility rules, you know, and you go further ahead and you see these where they're already given to you, and you see, oh, here I have PbSO4, it turns into a solid, which is not soluble, and you go back to other things where you're asked about solubility, and you see that there's a PbSO4 is going to be one of your products, then you know, okay, these aren't soluble, it's going to be a solid, and you can use little cheats like that to figure out what everything's going to be. So this one, this is a +2 charge, this is a +5 charge. There's like a -2 going on. Overall, And this is a +1 charge. SO4 is a +6 charge. So -2. Why does she keep writing -2? PB is +2 +6. And then +1 +5. And because there's no overall change in the charges, there's not a redox reaction. Okay, and so this is a +1 -1. This is a +1 +1 -2 going on over here. This is a +1 -2. This is a +1 -1. And because there's no real change, then it's not a redox reaction. Okay. And then we have to, is this our last problem? Oh, thank God. Okay. And then we have to balance the following oxidation reduction reactions by using the oxidation state method. So, this is exhausting. Being smart's exhausting. Just kidding. Okay. Magnesium, which is a salt, has a 0 charge. HCl +1 -1, it's aqueous, goes to magnesium 2+, +2 charge, obviously, it's at the top, plus Cl minus, -1, which is aqueous, plus H2, which is gas, and that's a 0. So this is a 0, and then now it's a +2. That means that Mg lost 2 electrons. And then hydrogen was a +1, and then now it's a 0. That means the hydrogen gained an electron. So now when we write it, we have to take that into account. We want to make sure the number of electrons lost by magnesium is equal to the number of electrons gained by hydrogen. To do that, we multiply H by 2. Magnesium will be multiplied by 1, so that won't actually really change anything. So oh my goodness, my eyeball. When we balance the rest of the equation, it's going to be like Mg solid plus 2 Cl or HCl goes to Mg 2 plus Cl 2 Cl minus plus H2. So then we have to look at the next one, which I'll pick a different color, is CO3 plus, which has a +3. It's aqueous. We have Ni, which is a solid. 0 goes to CO2 plus, +2, aqueous, plus Ni, 2 plus, aqueous, +2. So CO gained an electron, and I lost 2 electrons because it goes from 0 to a +2. Okay, so then the way you're going to rewrite it is 2 CO3 plus, aqueous, plus Ni, solid, this is an S, goes to 2 CO2 plus, aqueous, plus Ni, 2 plus, okay, because you have to balance out how many electrons are gained and lost. So then, the last one is similar, the same thing, where we have Zn, which is a solid, 0, plus H2SO4, which is an aqueous thing. It's got a +1, +6, and -2. It goes to ZnSO4, which plus 2 plus 6 minus 2. If you're wondering where like the 6 and the 2s or whatever are coming from, it's accounting for each element. Like zinc has a plus 2, sulfur has a plus 6, oxygen has a minus 2, H2 gas, and then Zn lost 2 electrons, and then hydrogen gained 1 electron. And I will leave you to the rest of the balancing for that. And that is how we do this worksheet. I hope this was helpful for you, and I will be sending out this shortly. Okay. Bye.